Hi, let me show you what we have been doing up to now. We are dealing with the combinational circuit synthesis. We explained the general way of doing synthesis for the combinational circuits in this frame. In here we examined the Ch4-2-4 method, which is based on the minimal function. How to find these minimal functions by using the Ch4-2-4 method has been examined here. Now I'm talking about this one now. This one is the previous one was the minimal function for the sum of product form. That means first canonical expansion. So we can consider now minimal functions in the form of product of sum. So we are going to define two minimal functions. One of them in the sum of product form 1, which is based of first canonical expansion. The second one is the one that I am going to explain now, is the sum of product form minimal function. What is this minimal function? This minimal function should be equivalent to the given function, and this minimal function must have minimal number of sum terms in it, and each sum term has got minimum number of variables in it, very similar to the other one. So on that definition, we are going to repeat the Ch4-2-4 method for this minimal function. So let's move up from here to open board. So open board. Okay, here we are. Now we are going to now Ch4-2-4 method for the sum of product form functions to find out the sum of product form minimal function. So in the previous one we had an elimination operation, which was that a prime plus a is equal to a. So this is an AND gate. This is another AND gate. Becomes only just one AND gate, and the fill in, since this variable is going to disappear, fill in is going to be reduced by 1. Now the elimination method for this new minimal function is going to be this one. These are the product terms in here, sum terms. So this sum terms and this sum terms, when they come next, when they considered at the same time together, this is equal to, use the Boolean algebra, this is equal to this one, that gives you 0, the result is A. So what is this in the design in terms of elements? So in here you've got one OR gate, sum term, this is another sum term, another OR gate, and the multiplication of these two OR gates. So it is something like that if you use this part. So if you use this part, it is just one OR gate which fill in is not going to have this small a variable, so number of input is going to be reduced by 1. Now the rest of them, so this is the operation that I am dealing with. The rest of the Ch4-2-4 method that I am going to use is based on this, but very similar. I am going to make the groups now, this time, consider it true max terms, not true min terms. When the function given to you, this is the true min terms because of that sum here. So you're going to transfer this through max terms. Max terms shows you where the function becomes 0. Sum of product forms, product of sum forms is related with second canonical expansion. In the second canonical expansion, we consider zero value point value function values. So these are the numbers tells us where the function becomes zero. That's why it is true max term. So we are going to make a table like that, considering the number of ones in the true max terms, not the true min terms. In the previous method, we considered these ones. In here, we are considering this one. Okay. So here you are. This first group has got one. There is no 0, 1 included group. Therefore, this is group 1, which includes 1, 1 in it. This group has got 2 ones in it. This group, 3 ones in it. That is all groups. So I made 3 groups considering these true max terms. So I'm going to compare some terms between the neighbor groups. Compare this 4 and 3, compare 4 and 6, and compare 4 and 12, and continue like that. After the comparison, how I'm going to do this comparison? By using this operation. This operation tells you one of the variables should be different values, while the other variables values are the same. Example, 4 and 6. If you compare those two, x3 is changing. Here you are. x3 here is 0. And x3 here is 1, changing. And the others, x1, 0, not changing. x2, 1 is not changing. x3 already said changing. And x4 is not changing. So that is, there is an operation like that. After the operation, x3 disappears. So that means the change variable disappears. And then what is left, 4 and 6, here you are. x3 has got a dash, x3 position has got dash. The other values, the common values, we wrote them. So after this operation, you're going to end up with this. So you can, in the sense of elements, so this is an OR gate, has got 3 inputs, x1, x2, x3, x4. So when it is 0, it's going to be itself. When it is 1, it's going to be prime. And this one for 6 is going to be another OR gate. x3 is going to be, so x1, x2 prime, and x4 are the same, and x3 is changing. So instead of those 3, you're going to use just one OR gate, which does not include that x3 variable because that disappeared. What is left is x1, x2 prime, x4. So this operation means in terms of elements, instead of this, use this. So if you continue this, you're going to find out the prime implicance, which is in the form of sum. So prime implicance, so when you're going to continue this until you stop. You cannot go any further. That means you cannot you cannot find any operation like that anymore. Then you stop. So you're going to consider now when you stop here, you see this one is one prime implicant. This is the another prime implicance. These are the sum terms corresponding to those two. Remember that when the variable value is 0, itself is going to change. So this is x2 comes here. In this one, x3 is one value. That's why x3 prime and x4 prime. So this is one of the prime implicant. This is the second prime implicant. When you write the prime implicants, from that you're going to find the essential prime implicants is the same method that we use in the previous example. So once you find the essential prime implicants, there are no, if you consider these essential prime implicants, all the true max terms are covered you see here 3, 11 and 4, 6, 12, 14. So if you look at this, all the true max terms are covered by those two. That's why that's the end of it. So you can write minimal function sum of product form, product of sum form is this, isn't it? X3 prime X4 prime times X2 prime X4. So that's the minimal function. So you see the minimal function, so you can do the comparison between the minimal function and the second canonical expansion form realization. You see you got 6 OR gates and fan-in is 6. Fan-in for the OR gates is 4. One AND gate is this one. This is the canonical form function realization. So if you write the second canonical function expansion for this function, you're going to have 6 sum terms product. So this is what I am saying, 6 OR gates. The fan-in each of the OR gate is going to be 4, the number of variables. And you got one AND gate, multiplication of 6. And the fan-in of this AND gate is 6. Now this is the minimal function. So for this minimal function, you've got 2 OR gates, comparing those two. Fan-in of these OR gates is, one of them is 2, the other one is 3. In here, both of them 4, all of them 4, isn't it? There are 4 OR gates. Each OR gate has got 4 fan-in. In here, 2 OR gates, one of them 3 fan-in, the other one 2 fan-in. And we've got one AND gate here, and the fan-in of this AND gate is not 6, it's just 2. So comparison is like that. So that 6 became 2, 6, 4 became 2, 3 less, and this fan-in became just 2. So drastically change. That's why we are finding the minimal function. So this is the minimal function. Finding the minimal function by using the Cohen-Mackey method. So that's the end of this video then.